Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover linear transformations. So in order to start that, let's talk about a mapping. And this mapping is denoted by T, which maps vector space V into vector space W. Now, vector space V is called the domain, and vector space W is called the codomain. And this is what we have here. T is going to map vector space V into vector space W. So what that means is if I have a little vector v in this vector space capital V, so this big blue space is called capital V, it's going to take this little vector v in capital V and it's going to map it into this vector space W, which is this. So, functional notation wise that we're used to maybe in algebra class is say T of V is equal to W, kind of like f of x is equal to y. So it has that same notation. So the range is actually a subset of this codomain. So what we know is we're going to take all vectors in this blue vector space V and we're going to map it to the codomain W. But it doesn't mean that you're actually going to fill the entire W. You could, you possibly couldn't. Sometimes you do, sometimes you don't. But what we do know is it will always be a subset of that. So this small little subspace right here, that's what I'm claiming it's a subspace, and we'll get there when we're talking about linear transformations. But this subset of this vector space is actually the range of the mapping. So let's talk about how to map particular linear maps, or even mapping right now. We'll talk about why this is a linear map. So T of V1 comma V2 is going to be equal to 3V1 is going to be the first component. 2V1 minus 3V2 is the second component, and then it's going to be V1 plus 2V2. So what we can see in this particular case is that this T right here is mapping R2 because this vector has two components, to R3 because this vector has three components, 1, 2, 3 components. So the domain space is going to be R2, and the codomain space is going to be R3 in this case. So they don't have to go from the same space to the same space. What you're used to maybe in algebra class is always going from R1 to R1. And maybe I'll show you a function as a mapping as well to show you it's really the same thing in a video, or maybe this one. So let's start with this. What is the image of this vector? So what I know is this is an R2 vector, and I know it's going to map into an R3 vector. So I want to know what is that R3 vector. What would W be in this case? Well, W is going to equal, this T plugging in 2 comma 3. So we're going to plug in 2 comma 3, and remember the mapping rule says it's going to be equal to 2v1, so 2 of those. So the first component is going to be 2 of the first piece. The second component is going to be 2 of the v1 minus 3 of v2. So this is going to be 2v1 minus 3v2. And finally the first component is going to be v1 plus 2v2. So v1 plus 2v2. So when we're done simplifying, what we get is this one is going to be, I should say this was 3v1, so 3v1. So this would be 6. This component is going to be 4 minus 9, so negative 5. And this was 2 plus 6, which is going to be 8. So this W vector, the output of this R2 vector is going to be this R3 vector. So maybe let's call it up. So this is going to be 6 minus 5, and then 8, which is going to be that vector right there. So really the idea is that this vector in this particular case is 2 comma 3. It is going to map to this vector W here, which is going to be 6 minus 5, 8. All right, now what about the preimage? Let's say if I have another vector in here. Now this vector would be in the range because all the blue is going to map to this yellow subspace. So this minus 9, minus 9, minus 1 will also be in here, and it's going to map somewhere back to the blue. So let's find the preimage. So what it says is that, t of v1 comma v2, our transformation is going to equal, this thing. So it's going to equal this minus 9 comma minus 1. So if I'm going to solve for this, well, I know the function rule for this, or the linear map for this, so it's this thing. So t of v1, v2 means that this is going to be equal to 3v1, 2v1 minus 3v2, and then v1 plus 2v2 is going to be equal to this minus 9, minus 9, minus 1. Now for an R3 vector to equal an R3 vector, that means the components have to be equal to each other. So this says, 3v1 would have to be equal to negative 9. That means the second component would have to match. So 2v1 minus 3v2 would be equal to minus 9. And then finally the last components would have to match. Now it's our choice. You could solve for v1 divided by 3, so v1 is going to be equal to negative 3 completely. And then once you know that this is equal to negative 3, you can solve for v2 as well. Or this is a linear algebra class. You could write this as 3, 0, negative 9, 2 minus 3, negative 9, and then 1, 2 minus 1. And then we can row reduce echelon form that, and then this will give us our solution as well. So it's kind of your choice on how you want to move through this system of equations. So 0, 1, 1, then 0, 0, 0. So as we know that if you solve that for v1, you're definitely going to get negative 3, and that's what this says. v1 equals negative 3. Plug negative 3 into here, what we're going to see is that v2 is going to be equal to 1. So that's what this says, v2 is equal to 1. So we know that this says v1 equals negative 3. This line says v2 is equal to 1. Or I can say that this v vector, v is equal to minus 3 and 1. So what I know is if I have a minus 3, 1, say over here, it's going to map to this vector here, which is going to be minus 9, minus 9, minus 1. Now if I was going to draw this, let's talk about image preimage thing again. So what I know is that it comes from R2, and then it's going to map it to R3. Now, if you've had a calculus 3 class, we do 3 dimensions like this. We have x, y, z. So, for instance, if I have minus 9, minus 9, minus 1, that's an ugly one. 6 minus 5, 8. Let's do this one. This will be a little bit easier to graph. So, 1, 2, 3, 4, 5, 6. There's a 6 on the x, and then minus 5 on the y. So 1, 2, 3, 4, 5, and then 8 on the z. So 1, 2, 3, 4, 5, 6, 7, 8. What we know is if we map this, this vector here by drawing essentially a cube, this vector right here is going to be 6 minus 5, 8. 6 minus 5, 8. And then what I know is that was mapped from 2, 3. So your image preimage thing, so 2, 3, that was mapped to this vector here. So what we know is that another way to look at that is that the transformation maps this R2 space to this R3 space. So it's going to map 2, 3 into this 6 minus 5, 8. Or very similar, if I was going to graph minus 9, minus 9, minus 1, that would map it back to 3, negative 1. So this would map it back to 3, negative 1. So this is the image. So this is the preimage. This is the image. So the image of 2, 3 is going to be this, and the preimage of this vector is going to be this. So a definition of a linear transformation. So let V and W be vector spaces, and the mapping T that maps vector space V into vector space W is called a linear transformation if the following two properties hold. So for any two vectors, U and V, in V, and any scalar C, we can say that T of U plus V is equal to T of U plus T of V, and T of CU is equal to C times T of U. So I want to explain what that means like graphically, and then we're also going to prove it with an example to see if something is a linear transformation. So what we know is if this is a linear, if this is a mapping, if I have u, what I know is I can map u to t of u. And also I can map v to t of v, so it looks something like that. So, you know, these lines are this transformation, this t that maps, you know, vector space v into, you know, vector space w. All right, now since v is a, you know, since this is a vector space, you know, vector spaces are closed under addition. So what I know is if I have a u and I have a v, I have a u plus v. Let's call it right here because I'm out of space. So this is going to be u plus v. Now I should be able to map every vector in the blue into this vector space w, and I sure can. So then over here is going to be, you know, the mapping, which is going to be, say, t of that mapping. So this is going to be equal to, you know, t of, let's do it in orange. So this is going to be t of that particular mapping. So t of u plus v, which, you know, is going to be a vector in vector space w. So u and v maps to t of u and w, and then v is a vector space in v, and this is going to map to a vector in w. It happens to be t of v. So these three vectors are also vectors in w. Now, what we know is since w is a vector space, that means if I have a vector t of v, and I also have a vector t of u, if I add these, t of u plus t of v, I should get another vector in here. And that just so happens to be, well, this exact vector right here. So this vector is also, you know, this is also equal to t of u plus t of v. It'll be exactly the same thing. So here's kind of the idea. What I can do is I can take two vectors in w, I can add them first, transform them second. So I can add them first, I can transform them second. That's what this first line says. Now, I can also do it this way. I can take the two vectors, I can transform them first, add them second, and that would be this. I can transform them first and then add them second, but it won't matter. I'll get the same vector every single time. I'll get this vector regardless if I add first, transform second, or if I transform first and add second. You'll get exactly the same thing. Now, this property also holds for scalar multiplication. So if I have a u, then I also have some c of u. Because it's a vector space, it's closed under scalar multiplication. Which means I can transform this vector, you know, your cu, into, say, here. So this is going to be t of cu. So I can scalar multiply first, transform second, or I can transform first and then scalar multiply second. So if I multiply t of u times c, I'll get the same spot here. It'll land in this exact same thing. So this vector right here is also c times t of u. So what I can do is I can scalar multiply first, transform second, or I could transform first and scalar multiply second. It won't matter. I'll get this vector every single time. Both ways. All right, so how do we, you know, algebraically essentially prove something is a linear transformation? And I guess let's go back to our previous example. So we had our example that looked like this. It said, let's prove t of v1 comma v2, which is equal to 3v1 comma 2v1 minus 3v2 comma v1 plus 2v2, you know, is a linear transformation. Let's say LT for linear transformation. So what I want to do is I want to prove it's a linear transformation, so I have to show both of these properties. So in order to do that, what I need to do is I have to define a vector u and also a vector v under this transformation. Now, this essentially is t of v is what we've defined. So if I let u, let's do it here. Let's say if I'm going to have u be equal to u1 comma u2, and then v is going to be equal to the vector v1 comma v2. So if I do t of sorry, if I do u plus v, what would we have here? Well, u plus v is going to be, u1 plus v1 comma u2 plus v2, because that's how we add vectors. Okay, so what I'm going to do is I'm going to show that t of u plus v, I'm going to show you this is equal to this. Okay, so let's start here. T of u plus v is equal to t of this thing. So this is going to be u1 plus v1, u2 plus v2. Now, the way we do the transformation says whatever's here, you're going to have to multiply by 3 for the first component. So this is going to be 3 times the first component. Well, the first component's this thing. So this is going to be u1 plus v1. And then the second component's going to be 2 times whatever's here minus 3 times whatever's here. So 2 times this, u1 plus v1, and then minus 3 times this. So minus 3 times u2 plus v2. And then finally, the last component is, this is supposed to be v1. Last component is going to be v1 plus 2 of these. So this is going to be v1, so u1 plus v1 plus 2v2. v2 is going to be this, so u2 plus v2. Now what I'm going to do is I'm going to algebraically simplify this thing by getting rid of the parentheses first, and then I'm going to try to write all the u's first and then the v's second. Let's do it one at a time. I don't want too many explanations, make it confusing. So here, so first parentheses, now remember what I'm trying to do is I'm trying to show that t of u plus v is equal to t of u plus t of v. So what I'm going to do for each one of these components is I'm going to write all the u's in first by using just a commutativity. So this is already written as the u terms first and the v terms second, so plus 3v. That first component's already done. But this one's not. I have uv, uv, so let's do the u's first. So 2u1 minus 3u2 plus 2v1 minus 3v2. So just a little bit of commutativity with addition and subtraction. And then similar u's first, so u1 plus 2u2 plus v1, oh, this is supposed to be a 2v2, so plus 2v2, so distribute both. Okay, now that I've done that, I know that I can break this apart into, I can say, I might be a little room here. So this is going to be 3u1, comma 2u1 minus 3u2, comma u1 plus 2u2. Let me show you what I was doing here. So what I'm doing is for the first component, I'm just going to grab the u's. Now the second component, I'm just going to grab the u's. And the third component, I'm just going to grab the u's. And now I'm going to add this, which means because I'm missing these blue parts, I'm missing this, this, and this. So I can write that as, this is going to be 3v1, comma, this part is going to be 2v1 minus 3v2, and then this part is going to be v2 plus 2. So 2. That should be a v1. I am messing this one up. Okay, good. This should be a v1 plus 2v2. Perfect. Okay. Forgive me. So boom, boom, boom. And this, well, actually, we already recognize this. This is just t of v. Therefore, this one right here has to be t of u. So this is t of u, and this piece here is t of v. All right. I also have to show that t of cu is equal to c times t of u. So let's start with that. Well, t of cu basically means, well, what is cu? I guess I didn't define it. Well, I think we know how to do this by now. Cu is going to be cu1, cu2, right? That's c times u. So if I can do a u plus v, I know that cu is going to be cu1, cu2. Just multiplying each component by c. Okay, so now what we do here is we follow this rule. This is 3 times the first component. Well, 3 times the first component, 3 cu2, so u1. This says 2 first component minus 3 second component. So 2 times the first component minus 3 times the second component. And then the last one says the first component plus 2 times the second component. So the first component plus 2 times the second component. Now, what I can do for each one of these binomial components is I'm going to pull a c out of this. So this is 3u1. I'm going to pull a c out of this. So this is c. This is 2u1 minus 3u2. And I can also pull a c out of this component. So this is c times u1 plus 2u2. Now for vectors, since all the vectors have a c in it, all the components have a c, I can pull the c out in front of the entire thing. So this is going to be equal to c times, well, this would be 3u1, comma 2u1 minus 3u2, comma u1 plus 2u2. And by definition, this is c times t of u, which means this is a linear transformation. This is true. Now I'm going to have a second half to this video because this will get longer if we continue. So this is what it means to be a linear transformation. So if you like the content, please subscribe.